When we convert a number into scientific notation equivalent, we'll think about moving a decimal point either to the left or to the right in order to maintain some order of magnitude in our number. For a number like 1,000, where there's no explicit decimal point, we can consider an imaginary one all the way over to the right. To reduce this number to a single digit in the ones place, with no digits after it past a decimal point, we would move that implied decimal point 3 digits to the left. That leaves us with just the significant value 1 multiplied by some power of 10. The power that goes with 10 is the number of skips to the left or to the right that we've made. If we've made skips to the left, that means we're trying to reduce something that was big, so the power is positive. An equivalent measure of 1,000 is 1 times 10 to the 3. For 45, likewise, there's no explicit decimal point, but an implied one that could be moved 1 space to the left. To maintain 2 significant digits, we can rewrite this as 4.5 times 10 to the 1. 6,525 could be rewritten as 6.525, maintaining all 4 significant digits, times 10 to the 3. 5,020 only has 3 significant digits in it. It can be written in scientific notation as 5.02 times 10 to the 3. Where an explicit decimal point is given, we need to move that either to the right or left accordingly to get just 1 digit in the ones place of a number that we multiply by a base 10. In 0.5, for instance, where we have 3 significant digits in total, we can rewrite this quantity as 5.00 times 10 to a power. Anytime we've moved a decimal point to the right, we're having to increase the magnitude of a number. That means that the number was small, and so moving to the right requires us to raise our power of 10 to a negative exponent. Similarly, in the quantity 0.0224, we can rewrite in scientific notation as 2.24 times 10 to the minus 2. For 0.000044, we can move our decimal point 1, 2, 3, 4, 5 digits to the right and rewrite this quantity as 4.4 times 10 to the minus 5. For 1.01, we can move our decimal point 1 digit to the right and rewrite this, keeping 3 significant figures intact as 1.01 times 10 to the minus 1. To rewrite a number in scientific notation as a numerical value, we'll simply move a decimal point accordingly based on the exponent associated with 10. In 2.62 times 10 to the 4, for instance, we're going to know that this number represents something very large, since the exponent associated with 10 is positive. That means that we're going to have to rewrite this number by moving our decimal point 4 spaces to the right. 1, 2, 3, 4. The vacancies are filled in by zeros. 26,200. Similarly, in 3.3 times 10 to the 2, we'll move our decimal point 2 spaces to the right. 1, 2. 6.022 times 10 to the 7 requires us to move our decimal point 7 spaces to the right. 1, 2, 3, 4, 5, 6, 7. Fill in vacancies with 0, and this is what we end up with. When we have a negative exponent, we know that we're going to reduce our quantity to a smaller number. So we'll move our decimal point to the left instead of the right. Our decimal point started here, we'll move it to the left 2 spaces and fill in vacancies with zeros. So we end up with 0.0727. In the next example, we'll move our decimal point 1 space to the left and end up with the answer 0.1024. Lastly, we'll move our decimal point 5 spaces to the left. 1, 2, 3, 4, 5, and fill in vacancies with zeros. In order to perform metric conversions, we're going to need to keep in mind all of the metric conversion prefixes that we've talked about in class. I'll show you a list of those. We use this metric prefix timeline as a means by which to determine how much different one metric unit of measure is compared to another metric unit of measure that measures the same fundamental quantity. For instance, if I wanted to convert 32 kilograms into grams, I would set up a conversion template just like this. My starting value, times sign and a line, equals my target value with target units. To get rid of my starting units, just like in a mathematical equation where I want to get rid of variables, I'm going to place starting units in the denominator of a conversion factor fraction. And target units will go in the numerator. In this case, grams are my target. I can use this metric prefix timeline to compare how many grams are in a kilogram. I know that every skip that I make along this metric prefix timeline from one unit to the next is worth 1,000-fold, with the exception of centi, which I've starred here. Remember, centi is only worth a skip of 100 to the right of a base unit. In this case, I'm going from grams to kilograms. I know grams are my base unit, and if I skip to the left one spot, I've increased my base unit by a factor of 1,000. That must mean there are 1,000 grams in every 1 kilogram. And to determine the number of grams in kilograms, I multiply by 1,000. 32,000 grams in 32 kilograms. In the next problem, I want to determine how many milliliters are in 5.02 liters. Again, I can set this up by allowing units to cancel top and bottom, placing liters in the denominator, milliliters in the numerator of this conversion factor. Here, liters are my base unit. I know that I have a skip over centi because, again, centi is the weird exception to this rule, of 1,000 to get to the prefix milli. But I've skipped to the right. That must mean that I'm getting smaller. There are 10 to the 3 liters in every 1 milliliter. Or another way to say this is that if I did just the opposite, a skip from milli to a base unit makes me go by a factor of 1,000 to the left, 1,000 milliliters in every 1 liter. So I could just as easily rewrite this in this way. 1,000 milliliters in a liter. Either way works, because what we'll end up with at the end is 5,020. To convert 7.3 megameters into meters, again, we'll get rid of megameters, have just meters on the top. Our base unit, meters, requires 2 steps to get to the prefix mega. That's a factor of 1,000 here, and another factor of 1,000 here, or multiplied together, a factor of 1,000,000. 1 times 10 to the 6th power. There are 1 times 10 to the 6th power meters, therefore, in every 1 megameter. We'll end up with 7.3 times 10 to the 6th meters in 7.3 megameters. Converting meters into nanometers requires us to think about the skips from a base unit of meters down to nano, which is a factor of 1,000 to get to milli, a factor of another 1,000 to get to micro, and yet one more factor of 1,000 to get to nano. In 1 nanometer, therefore, there are a factor of 1,000 times 1,000 times 1,000 smaller magnitude meters, since we've skipped to the right. 1 times 10 to the minus 9 meters in every 1 nanometer. Or, another way to think about this again, 1 billion, or 1 times 10 to the positive 9 nanometers in a meter. Either way, we end up with 6.50 nanometers in 6.50 times 10 to the minus 9 meters. To convert 2.70 times 10 to the 6th micrograms into grams, we'll get rid of micrograms and put grams in the numerator. We'll use our metric prefix timeline to show us that to skip from grams, a base unit, to the prefix micro requires a step of 1,000, another step of 1,000, for a factor of 10 to the minus 6th. There are 1 times 10 to the minus 6 grams in every 1 microgram. Multiply this through, and we end up with 2.70 grams. and 2.70 times 10 to the 6th micrograms. Lastly, to convert centimeters into millimeters, we'll take note of the oddity, an exception to this general rule of our prefix timeline that tells us that the skip between centi and milli is not a factor of 1,000. The skip between a base unit and centi is a factor of 100. To get to milli, we need another factor of 10. That means that there are 10 millimeters in a centimeter, or there are 10 to the minus 1 centimeters in a millimeter. Either way we think about this, whether there are 10 millimeters in a centimeter or a tenth of a centimeter in a millimeter, we'll have to multiply this by 10. We end up with 6.02 times 10 to the third millimeters and 6.02 times 10 to the 2 centimeters. What we've been doing all along has been establishing identities that help us move from one unit into another. In the next set of problems, we're given identities and asked to employ them. So here we don't have to worry about a prefix timeline because we're given information that we need straight away. We'll set up templates just like we did before. For example, in Part G, where we want to convert pounds to kilograms, we'll need to look for a relationship between pounds and kilograms. Oh no, we're only given information about the relationship between pounds and grams. Well, luckily, we already know how to go from 453.6 grams into kilograms. According to our metric prefix timeline, there are 1,000 grams in every 1 kilogram. So anytime I see 453.6 grams, that's exactly equivalent to 0.4536 kilograms. Multiplying that by 122 gives us the 3 significant digits, 55.3 kilograms. In example H, we want to go from inches into centimeters. So we'll use the identity given above that 1 inch is the same as 2.54 centimeters. Multiply it through and keep 2 significant digits, and we end up with precisely 30. How do we get 2 significant digits out of something that's precisely a number that ends in 0? Well, 2 ways that we can do this. One, we can either add a decimal point to the end of that number, 30 with a decimal point after it, has 2 significant figures, or we can rewrite in scientific notation as 3.0 times 10 to the first power. In example I, we want to go from miles into kilometers. We're given the relationship that 1 mile is equivalent to 1.609 kilometers. Multiplying through and keeping 3 significant digits, we end up with 4.99 kilometers, about 5K. Lastly, to go from gallons into liters, we'll use the relationship given last. 1 gallon is worth 3.785 liters. Keep 2 significant digits, multiply through, and we end up with 15 liters.